Hello and welcome to Func Prog Sweden. Warm welcome everyone, and today I have a guest in the studio, actually presenting from Stockholm. So welcome. I'll head over immediately to the agenda. So first up there will be a short intro by me, Magnus, and then we'll head over to my guest in the studio, Intro to Swift for Functional Programmers by Adrian. And after that presentation, we'll head over to Polynomial Functors, Jackpot by André. So he will join us on link from Gothenburg. But first, I would like to thank our video sponsor, Adabeat. Adabeat is an IT consulting company focusing on functional programming. And if you want to know more about Adabeat, check them out on social media or on adabeat.com. Also, the coming schedule, we haven't set dates for August, September. However, we know that on 10th of October, we will be IRL from Kivra in Stockholm. So if you're in Stockholm in October, please join us in Kivra. If you want to support the MeetUp community or Func Prog Sweden, head over to MeetUp and join the MeetUp community. Or make sure to follow us and subscribe on the YouTube channel. And last but not least, also if you want to join in and discuss functional programming and the meetup today with other functional programmers, head over to our Discord server. You'll find the links and everything on the meetup or on the YouTube channel. As always, if you have questions during the presentation, just shoot them in the YouTube chat or on the Discord server. With that, we will start with our first presentation. Warm welcome, Adrian. Sorry. Yeah, my brain got confused.
That's
2 A's. Yeah, sorry. Adrian, warm welcome.
Thank you.
Thank you very much.
Swedish spelling, so I'm not used to it.
Yes.
Cool.
Now we'll do the trickiest part in this presentation. I'll give Adrian the cable and we hope it works.
It's probably harder than with them also. But
Adrian will also do live coding, so we'll see how that works.
A little bit of live coding.
Yeah, a little bit of live coding. So,
yes, here we go.
Yay! Welcome, Adrian. The stage is yours.
Thank you.
You're welcome.
Yes. Intro to Swift for functional programmers, or you could also call it Intro to Functional Programming for Swift people, I guess. You know, you could flip those things around. My name is Adrian. Or Adrian, or Adrian, or many other ways of saying it. I work as an iOS developer at. I'm employed by Blocket, but I work for Shipset, you could say. Most of the things I do are for Shipstead, which is you could find me on Twitter and GitHub or everywhere else where my name is. And I happen to have seen one of the talks here, or many more, but one of the one which, let's say, inspired me to make one for Swift was Intro to Rust by Michael Snoyman, if I'm pronouncing it correctly. And I thought that Swift deserves a little bit of love as well from the functional programming community, since it is, there is many things you could do in a bit functional way in it. So here I am. Cool. So let's go to the first slide. What is Swift? Swift is a high-level, general-purpose, multi-paradigm, blah blah blah. But basically, it's it's a language made by Apple to replace Objective-C. So they had very, very ambitious goals with it because, well, you gotta basically convert your whole developer base, and that's quite a lot of people, to a new language. And one of the things they said, or it says on the Swift.org, and I believe in some hidden forums when they all started it, was that they want to make programming simple things easy and difficult things possible. And this is a way to say that they have a thing called progressive disclosure they try to abide to, meaning that you could do simple things in it. And I mean, you could do things in it without knowing that much, but the more you know it, the kind of more complex it becomes. But my goal of it, like if there is something you would take out of this talk, is that there is not much you need to know in order to start with Swift. And when you need those powers, you can reach them later on in your career. Yes. Second one. Why is Swift relevant to a functional program MeetUp? Well, Swift has immutable data structures, first class higher order functions, product and sum types, type safety, strong typing. That's not necessarily a functional programming thing, but it's highly valid sometimes. You have both lazy and eager evaluation. Eager, it's by default eager. You have quite powerful pattern matching, and much more, which we're not going to go unfortunately today in, but there is more to it. We have to start with a hello world because it's a programming language. So let's see how we do that in Swift. And I am gonna do a little bit of light coding, not too much. I have stuff. I'm gonna show you some stuff which is live coding, but it's not the main focus. The main focus is to understand the syntax a little bit. So that's how you write a hello world. And I'm now in Xcode Playgrounds, which you can it's the Xcode environment. Unfortunately, you do have to usually have a Mac when you're developing on Apple platforms. You can't really do that on Windows. That's the sad part about it. You can run it on Windows, but you can't really, it's not a thing to develop Swift on other platforms just yet. Not yet. Yes, so that was it. That's how you write hello world in Swift. And here we can see the actual output. So this is running code in Xcode Playgrounds. So one of the advantages is I could make a presentation straight into it, which is great. Yes. Moving on. We're going to talk about immutability. And I put optional in parentheses here because this is encouraged, but not, let's say, it's not like in Haskell, right? You have a choice to have things which are immutable and mutable. How do we define things which are immutable? Well, let, we say the name of the constant in this case, not a variable. We don't need to specify the type most of the time. So if I would say something like this, it would work just well. And this is a way, this is like one of the simplest things you could do in this language, and it's already immutable. I cannot change the data inside this constant because, well, the compiler tells me what's wrong. Another interesting thing about this language is that it kind of encourages you to start with immutable things and then move to mutable ones. And I'm going to move on to structs, which are product types, which I'm going to explain later. But it's still interesting to take a look at them at this moment, because if I say something like, let's say, struct foo, bar, and let's say this is a string, if I try to make an instance of this guy, and I'm going to reuse a variable, and let's say that this is, again, foo, I cannot change this either, which makes sense because you have a let in here. But still, it's in most of the Apple tutorials, in most of the info you get on the most articles, or kind of the whole thing around the language is that you're supposed to have some sort of like you gotta start with structs. No one really knows why, but it's a thing. And I mean, I do have a hunch. Why is it so? The reason is because this language is trying to kind of nudge you into the direction of having value types over, have value semantics over reference semantics, and having immutable data over immutable data. That's very tricky to accomplish because the language itself set to replace Objective-C, which is a very dynamic reference, kind of referencey, or whatever you call it, kind of language. So it's quite a paradigm shift. But let's move on. So you have optional immutability. You can have things which are mutable as well with a var, and in that case, I would be able to change it. I still need to make this a var too. But now we have mutability with value semantics. So now this works. Functions and higher order functions. Maybe I should have started with functions since we're in the functional program meetup, but let's look at the functions now. I'm going to copy paste some snippets, so we have something to work on straight away. Or functions. Let's look at the syntax. Here we have the keyword, reserve keyword. We have parameters. We have the return type. And we have the body of a function. It's a C-based language. You can omit the return if you have a simple enough expression. And let's look at the next one. The next one is what we are interested in this kind of, the reason why we're here, to understand, I guess, higher order functions. What's a higher order function? It's a function which takes in functions, returns functions, or does both of those. And in this case, we can take in a function. So Swift does support that. And interestingly, it can support also returning functions. So here we have, you could call it, I guess, a curried version of apply twice. How do we use this? Well, you can call them with a number, let's say 5. You could also call it, you can pass in the function as a parameter. So notice that there is no, I don't need to expand on it. I just pass it in straight away, which is it's really handy sometimes. And you could also do this, pass in the 5 as a parameter. And now this is going to be, well, it's not a function yet, so I gotta, doesn't return anything yet, I meant. Now it's going to return something. So now we're using apply twice curried. So that's how you use functions in Swift. I would say it's pretty neat. You can do things which are a bit more usual to other functional programming languages, like maybe make here I made a closed range. Then you could map on it. You could pass functions like this, and you're gonna get the result. And you could continue on that, and maybe I don't know why this is not showing correctly, but you should have showed the right numbers. I guess it's because of the presentation size. But you could continue training on transformations, and that's where the feeling of kind of functional programming thingy from the language is coming from. It's slowly nudging you in that direction. Yes. There's another thing which Swift supports, which makes it friendly to functional programmers, and that's lazy evaluation. Lazy evaluation is, so by default, Swift is eagerly evaluated. So it evaluates whatever you have in here straight away. And even if you have like a huge array and there's some computation in it, it's going to evaluate it straight away. Let's look at an example. So for lazy functions, I have the, I guess, stereotypical is prime calculation. I mean, it could have been anything else in here. The only thing I cared about when I came up with this is that this takes a little bit of processing time, even on an M1 Mac. And I do define a range of numbers, immutable range of numbers. Not that it matters at the moment, but you could imagine not needing any of this. You could put all of this in like some sort of long, statement, kind of like ignoring all the variables or constants in this case. And the interesting thing to look at here is how this executes. So if I'm going to run it, it's going to go through the whole closed range of numbers. So here we have a closed range for a bit better visibility. This means basically all the numbers from 1 million to 1,500,000. And what it's going to do is going to go through all the numbers, filter it on this function, which takes in an integer, returns a boolean if it's prime or not, and it's going to return me to us the elements which are prime. But let's say I only care about don't know, first one perhaps. Let's do that. If I would care only about first one, I would do primes, or maybe if let, which I'm gonna explain. First prime, primes, and then first. If I do that, and then perhaps reference it, see what happens. It's still gonna go for the whole list, even though I only care about the first one. And that's not always what we want. Sometimes we just want, the first one, and we don't care about the rest of the computation. And Swift has opt-in laziness, and it's quite simple to use if you know about it. You just drop a lazy on the, in this case, the closed range. That's gonna make this computation stop, straight after finding the first element, which is also, I would say, quite important for some, for functional programming sometimes. That's laziness. I did promise I'm going to explain what is if let, and I will do that, I promise. But let's go to the next slide where you're going to have a little bit more of this. Here we go. Product types, sum types. Let's start with product types. Initially, when you start learning this language, you never really hear any mentions of what's a product type, what's a sum type, and in some way I think it's a good thing, because if you would start trying to understand it, of course if you don't have a functional programming background, which I didn't when I started learning the language, but it's interesting to think about it, about algebraic data types, and the reasoning for that, at least for me, it was that I could make impossible states, like states which should be impossible at compile time, which is something which Swift excels at as well, because the compiler here is quite helpful sometimes. But let's look at a bit more, perhaps theoretical, but I would say quite neat example. So if I would go back to my bag of tricks and pull out a new trick, I'm gonna pull the one which is gonna say product types. Here we go. So what are product types? Product types are a combination of our types, I would say, and the combination is basically how many instances of that type you could make. And the reason why I decided to add this in the presentation is because I thought it would be quite interesting to look at this from for perhaps some people which see Swift from a new angle, let's say, like this. We can have, if we have a product, and these guys are generics here, and we define those generics as booleans, there is 2 by 2 states you could have. And the reasoning is that, well, you have true, true for the first one, you have true, false for the second one, and you end up with true, 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 false, 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 true, false, false, and that is 2 by 2 equal 4. That's all the possible ways you could make this product when generalized with booleans possible. Another interesting thing I would say available in Swift is called void, and void in this case does allow you, so it's not the same as in some other kind of functional programming languages, like in Haskell, from what I understand, it does not let you instantiate anything, like it's just like a empty void. Here it is kind of, it does let you make something with it. So I can generalize product on A and B, and I can make the second generic type a void, which still allows me to instantiate it. So that gives us true, false, and in both cases we don't have any choice but put void in here. Now the most interesting one, which the whole kind of the whole mystery is getting revealed here, I would say. There is a type which most Swift programmers I would suspect never seen, just because you cannot not do anything with it. It's called never, and I have not seen this myself for for a really long while until I happened to catch this explanation from some other people explaining, okay, never corresponds to 0, and I was like, why? Well, you cannot make anything with never. And never, if I generalize product with a bool and never, kind of nullifies the whole thing. Like, it maps to the algebra which we had in school, in simple algebra which we had really long time ago. Like, you cannot make a product type with a bool and a never, because a never cannot be made up, and nullifies the whole thing, and it's kind of like a 0. So that's where it starts to make sense if you can map this to math. My math teacher would have never believed I would ever end up explaining this to anyone. So I'm quite surprised myself, but that's basically a way to look at it. Some types are similar, but here we have addition, because you could either have something on the left or something on the right. And we're going to do the same exercise of deriving what we can do with this, and let's look at the first example. So first example, it's a bit tricky to, it kind of tricks us a little bit, because we have the same result. You have 2 plus 2 by 4, it's 4, and before we had to multiply by 2, it's 4. So it's kind of same number. I mean, why should we care? But I mean, if we follow the things we can do, we end up with true false for the left case, we end up with the true false for right case, and that is indeed 4 cases we can make this sum with. But here where it gets a little bit more interesting, since we can have either left or either right, we can stick some values into it, and this is our associated types. I forgot to mention that. You can stick values into your enums, and you can pass them around. Then you end up having left, true, false. Right one can be only void. There is nothing else you put it in there, and that's 2 plus 1 equals 3, which also corresponds to the simple math we had in school. And the last one, 2 plus 0 equals 2. And I guess you could see by now where this is going. We cannot have anything in here. It just does not work. And since we have only 2 types, 2 instances of this type, we end up with 2 plus 0, because we cannot do anything with the right one, and that is 2. So that's a bit of an intuition, and I guess for people who have done quite a lot of functional programming, this is maybe quite basic, but still interesting to look at. I do hope there is some people which have looking at Swift from a new angle today. And why this matters? Well, you can argue a lot why it matters and why it doesn't. What I like about Swift, it does not lock you into this from the beginning. Like, this is not knowledge you need to know in order to use Swift. Like some other languages out there, they kind of guide you along. You can do a lot of stuff without understanding any of this, and that's kind of a benefit of a language. I'm not saying it's the only language which does that, but I think it does it well. And as I said before I moved to pattern matching, one of the reasons why thinking in terms of product types and sum types is interesting is because you can make impossible state. You can define that on the code level rather than doing a lot of if else, maybe that or maybe this. There's an example. There's a really interesting example in your old session, which I'm gonna steal from a resource. If we would pass in a URL request, we would get a data, a question mark, URL response question mark, error, and then this is a closure or like a function. But the interesting thing is that you can have an optional data, optional meaning that you might have data or might not have data. You might have an URL response, you might not have an URL response, and you get an error as well. And it's maybe now you see that there's something wrong with this. Like, what if you have data and you have error at the same time? I mean, that's technically possible. But if you think about modeling your I mean, data model, you could call that. You could call it like that. Then this kind of stuff might not be. You make it impossible at compile time because you could stick here in sum type and enum. And this is Apple's APIs, and I'm not criticizing them. I'm passing around the, just observing things which are interesting. As I said, I did take this example from a very interesting resource. I highly recommend algebraic data types from Point 3. That's where I first saw this stuff, and I highly recommend people checking it out. And I'm going to have this talk on GitHub later. You could check it out. But let's move to pattern matching now. So pattern matching is one of the things in Swift which Swift is known for. I don't think we have... I mean, there's so many ways of pattern matching Swift that it would take a whole talk in itself to do that. So what I'm going to do is just to do the simple ones, or simplest version of it, and then one of the more complicated ones a bit later. So if we would switch on a sum, we could, switching on a sum means that we go either left or right, in this case, because we only have 2. Or first, second, depends how you take it. And we just follow what the compiler says. We can bind to the values, to the associated values, and do something with it, perhaps just reference it. And we could maybe ignore it here because we don't care. And ignoring it is done by saying break. That's basically how you would do that. That's pattern matching, super simple pattern matching. There's a little bit more complicated pattern matching, which I'm also going to just paste in because it's tedious to write all of that. And that would be, let's see, 5th, pattern matching point. You can pattern match on an expression, or like it's called expression pattern matching. This is a tuple, which is also a product type. You can have anything in here. You could put a string if you want. And in this case, we are pattern matching on the tuple itself, and we're saying, okay, well, what if it's 0, 0? In that case, we reach this branch of code. What if it's in this range? So you're pattern matching on a range. That's I don't know how many languages can do this, but I would suspect it is a little bit of a, I mean, depends on what you look at. Of course, there's way more powerful languages, but it's still interesting that Swift has this. And I think it had it from the beginning when it was released in 2014 or 15, I think, was one of the first versions. Yeah, so that's pattern matching. And error handling. Let's move to error handling. Error handling takes multiple variations in Swift. There is kind of 2 ways to do it. There's still no clear path, which one is the right one. People kind of mix and match sometimes. And I would say the first one to look at is the one where you throw from a function. So if a function happens to say that, okay, I could throw this error, which is the network error. Here we just have some boilerplate to make something happening on the screen. And the way to deal with this is you need to open a do catch syntax. So you have do catch like in some other languages out there, and then you're going to call your throwing fetch, and then here you could say some URL. The interesting thing is that compared to some other languages, or compared to most of the other languages which have this, I'm going to comment this out, which have this syntax, these guys do catch, they don't unwind the call stack, meaning that it kind of treats this throws as a return from the function itself. So this is basically a return under the hood. So it's not like it's quite performant to do this kind of stuff. So you shouldn't be afraid of it if you do it in Swift. It is though a little bit. It infects your code if you like you need to short circuit it at some point, and you do need to have. So Swift is very like strict about what you can do. So you do need to specify throws if it's actually gonna throw. So you can't just randomly throw an error from a context which cannot throw an error and so on and so on. So that's the interesting thing about this language. But let's see what we get here. Do we get an error? Now we got an error. Now we got an error again. The bull god today is sending us errors. Let's look at the unthrowing version of fetch. You can pass errors as a embedded in a sum type in this case, and the way to do that is, well, you could see it on the screen. You just have a bool random, then you embed it in a success, and then you can put it into a failure as well. So that's just basic error handling in Swift. This version, I do prefer it a little bit more because you stay in the land of types, I guess you could say like that. But it is tricky because, I mean, I think it's a matter of preference. It's just that both of these ways, they don't support accumulating errors as far as I know. So you wouldn't be able to pass in like an result of array of errors like this. There is some libraries which are trying to fix that, and one of them is validated from the same 0.3 co people I mentioned before. So yeah, there is ways to handle errors in Swift. You're not gonna be full of errors if you use this language. And I guess one more interesting to mention is that you don't need this syntax. You could also do this, which means that I don't care if this fails or not, unless I need the value. And then you could, this is going to turn out as an optional value, and here I need to unwrap it. But if I don't unwrap it, if I don't unwrap it, then I'm going to have it just as an optional type, which means that it can be a nil, a string or a nil, which makes it actually another way you could argue of error handling, because it could have a nil or it could have a value. But that's very similar to what the result is giving you. So I guess it's the same type of error handling. It's just that optionals are, one more way to do it. You could also force unwrap, meaning that this would crash at runtime if it happens to be an error. If it happens to throw an error. This sounds a little scary, but sometimes you might actually want to do this if you're loading, I don't know, assets from a disk and you don't want your application to work. It cannot work without those assets or something like that. So it has many ways to handle that. And that was error handling. Should we move to the demo? I think we can move to the demo. The demo is going to try to apply all of the say tricks we learned, and hopefully all of them are going to be used. Meaning, like you can see, it was really daunting to try to make a statement for this language. You could say that in like less than 1 hour and try to prove it that it's interesting from a functional programming point of view. Or maybe you could flip that around and for someone who's just doing Swift to look into functional programming. And the demo itself is not that focused on functional programming. It's just the usual Swift code. But it does keep in mind some of the principles, like, I don't know, keeping the data separate from the mutations and so on. But that's just a general thing in Swift, I guess. So what are we going to do? I took the, we have the NASA API. I'm going to look at some pictures, hopefully, if we get to them. And I took a chance to model the response we might get from NASA. Or the response is going to have an explanation, which is a string, string, string. Coding keys are a way to specify, to kind of, like, if we get the JSON back in a form which is not the way we want it to name our types in Swift, because we would want to use a camel case in here. We would do this, basically. Say, okay, I have a coding case and string, and if whenever you see this one, actually match it internally to this representation. And decodable is a protocol. Protocols, we're not going to get into protocols today, but protocols are, you could call them interfaces in some other languages. They're a bit different. It depends on which language you're compare it with, but it's a way to extend the language. And I mean, some protocols are provided by Apple or by the foundation, by Swift itself. But you can extend the language in a way that you feel that it makes sense for your use case, and it would be for the language itself. It would not make a difference if that's your protocol or if that's something which was coming with the language itself. So it does not have a lot of compiler magic. I mean, it does have compiler magic, but you can play with it in a way. You could define your collection type, for example, your own custom collection type, and it would behave exactly the way as any other collection type in Swift does. And that's done through protocols, and that's a way of composing functionality in it. I did not mention that, but yes, this language also likes to do composition over inheritance. It's also a thing from the ground up, which is also something which might be interesting from a point of view of functional programming. But let's go to the demo. I've been talking too much. Yes, what do we have here? I'm going to paste in some boilerplate, because no one likes boilerplate. And that's some way to do decoding in Swift. Fetch data and decoding. Don't get scared of the amount of code. It's just the presentation mode makes it look a lot more than it is. But there's also a way to make this simpler, but we're gonna get into that later. Let's see how we fetch some data. We pass in an URL. We return the result, which can be data or error. This guy is provided by Foundation, which is part of Swift Foundation. Then we're going to call URL session, which is also a thing provided by basically the Apple platform. I guess it's everywhere. We're going to return a success, and then we're going to catch if we get an error. We have some new keywords here, which I'm not going to go again into it fully, or I'm just going to say a few words about it. You can do structured concurrency in Swift since, I believe, 2 versions ago they implemented it. I'm not sure exactly which one, but this is a new thing. So, and it's not similar to what you would imagine it looks in languages like, I don't know, JavaScript. It's a little bit more like Rust, meaning like they try to bake it in the same philosophy of like trying to make things impossible at compile time. So we would, that's like a very short intro of what async await is. And it is a way to do asynchrony. So that's I guess that's also a way to say what async await is. We're gonna decode some the response, and the way this works is, since we marked this guy as decodable, then we can decode it, and it does not have to be JSON. It could be some other stuff as well, as long as there's a way to send it through, like in some sort of form which is not code. And we tried to decode it. Well, we got a success, we got a failure. Then here we're going to create an image. And the UI image is something provided by Apple as well. I mean, everything here is provided by Apple, but it's part of UIKit, which is a framework for developing apps on iPhones, macOS, and well, AppKit for macOS, but you could use it still. Okay, let's do something now. Then let's do some coding. So we need to fetch some data. We have URL up top. Let's see what happens. Well, it tells me that I need to await it because I'm in a context which does not support concurrency. And now it works. and we got a success back. And all of this is live. The stuff you're seeing down here shouldn't be too scared of. This is just Xcode being Xcode. It does work actually, but we are way behind the other IDEs out there, but we gotta work with what we have. What can we do next with it? So let value maybe. We got an data in there. What can we do with it? Well, we can pass functions like this. And I guess, what should I do with this one? We have a data. We need a way to transform it and get something else. Maybe I should pass the decode response, which I have right there. And I do pass it point free style, and I think I'm gonna get some result. Hopefully. And we have a double result. And so most of the people which have seen, I don't know, have seen this kind of stuff before know already the answer. We actually need to flat map on it, and that's gonna flatten the structure. Now we have a result of response and error, which we want in this case. And just to make sure that it does what it does, yes, we have a success and we have some data in there, and Xcode is complaining, but we're going through. Let's switch on this. Switch on the value. We have a success. We're binding to the value, and in this case, the response. And let's see what the response has. It does give us an HD URL, which in this case is a string, but yeah, we're not gonna handle errors because, well, don't know. I've not seen a live demo of anyone handling errors, so I guess I'm gonna keep the the tradition. What can we do next with this? Well, we have let's assign it to a variable, or constant in this case. HD URL. We have an HD URL. It does complain because I need to, I think I need to make it a computed variable. Well, we don't really need to do this actually. I don't know why I'm going that direction. I'm just trying to do things in a bit different way, but I guess we could just go straight here. I'm gonna fetch the data yet again from the URL. Let's make the URL itself. So as I said, Swift is very, very particular about what you're passing it in. If you pass like a string to something which wants an, like we want to make an URL in here, and it is gonna complain. It's not gonna let you do that because, oh well, that's an option. Here we have to have an exclamation mark, meaning that if this initializer fails, this is gonna crash. You could also just not do that and just unwrap it, and that's gonna give us like a safe path to it. And now we have an honest URL. But since we're doing a live demo, we don't really care about that, so we're just gonna force unwrap it because we know we have an URL in here. And that's the next thing. We fetch the data again, and here we're gonna have some result, result. Let's see what we get, and I need to do await yet again. I believe this should work now. Here we have result of data in there, and hopefully that's the image somewhere inside. I think, maybe. No. I have no idea. I haven't clicked on that, but now I clicked on it. So that was it. That was a longer version of doing it. I could also show a shorter version of doing it without all of this code. There is a way to do it, which it would have been really hard to read for someone who's seeing it for the first time, and that's basically that version. You don't need a lot of code to do things in Swift. That's my main goal for this talk, to try to explain that this language is not doing anything, like you don't need to know much of it to do things like this. That's me, yet again. You can find me on Twitter, GitHub, LinkedIn, and everywhere. I have some references I want to share with you. A Swift tour by Swift, structure concurrency as well on swift.org, I believe. Collection types is one of also the highlights of this language and what it can do. Point3.co for people which are interested into functional programming and Swift. And with this, I think I'm done.
Thank you very much, Adrian. Thank you. Very nice presentation. We had some questions in the beginning, like are list collections immutable type? But someone else, Gabor, answered it. It depends on if you assign it to a const or a variable.
Thank you, Gabor.
Then we had a shout out also. I'm surprised by the functional support in Swift. Cool stuff from Douglas.
Thank you.
So I think you managed to convince someone.
That was the goal. I wasn't trying to do anything, complicated.
Yeah.
It was interesting to see the other talk about Rust
Mm?
from the functional point of view, and I thought that it would be interesting to do the same for Swift, and I think it deserves a little bit of attention there.
It does. It does. It's really nice.
Cool.
Yeah. How come you came into Swift in the beginning?
I mean, that's like,
Was it just a coincidence?
I don't know. I think I think I was one of the victims of progressive disclosure. Like you can do simple things with, like you do things with it which do not require a lot of knowledge, but then, the deeper you go into it, you have to...
You learn more and more as you progress in your
Yeah.
career.
Sometimes you learn things you don't want to learn about. There's a funny thing about Swift. It's like simple, but it has... I think it's top... I don't know exactly which... what number is it, but I know it's top languages in amount of reserved keywords.
Ooh.
So, like, there is so much in it, which, like, someone who has seen this language 5 years ago, and you would still he or she would still understand what I'm doing here, but going into like a real project, people would feel like, oh, that's a different language. There's a lot of you could argue in both ways. It's a good thing, it's a bad thing, but it's lets you do things as I proved to you, hopefully.
Yep.
Without knowing much. But if you want to do more complicated things, you could do that as well.
Yep, cool. How come you come into functional then? So you started out learning Swift, and then, like it said, took one step at a time, and then at some point you just unraveled or or stumbled.
I think it was a happy accident.
Oh.
You could call it happy accident. Like as I said, I have never been like a big math kind of person, or like someone who would care about mathematics in school or in general in life. But I think when I saw once that you can, the things I've been doing in programming up to that point, you could simplify them in a way that you could provably you could have like a pattern for how you could do things in a way that actually makes the code a little bit make more sense, and there's like a rule set around that, and there's some guys in like 70s who figured out all of this stuff before you. It kind of like, I was like, okay, that's interesting, and then I started looking at the programming itself a little bit different way, because now I can look at my my own code, and there's things I'm doing in it which now I'm doing in a bit different way, because I'm thinking about all of this. Okay, should this be even possible to write, right? That's something which comes from functional programming. It does push you into, I don't know, I would say in a better way of designing software. Not always, but
no.
Most
I kind of agree. My own career in software development was starting elsewhere and then ending up in Erlang. And then once I learned Erlang, or functional programming, Erlang and then functional programming, really start seeing coding in another way.
It's one of those things people come into functional programming, but they don't leave it. Like
it's the end.
No, I mean, like
the end state.
Yeah, I mean, you come into it and you're like, okay, maybe you get it, and you get it, meaning like you like what's happening in it, like the way you build stuff.
Yes.
You don't feel like dropping that after you know it. That's what I mean.
Agree.
It's a good thing. Not always, because sometimes it's a little bit verbose, sometimes it's just not what you want. But if you would talk in general, it gives a little bit of aesthetics to what we're doing.
Yeah. Again, thank you very much for joining us, Adrian, and for your presentation. We'll put out the links, as Adrian mentioned. We'll put them out below the video and in MeetUp, so you can find it there also. for those who are interested in your presentation. And once you put it out on GitHub, we'll share the link there also. Of course, again, thank you very much, and thanks for your participation.
Cool.
With that, we'll head over to our next presenter for the evening, André. Welcome, André.
Hello, can you hear me?
Yeah.
All right.
We hear you. Yay, welcome, Andrea. And I'm
Thanks.
really happy
Thanks,
to
Magnus.
say that. Yeah, you're welcome. You're actually a colleague of mine, so I'm super thrilled that we colleague. And also, I'm going to go ahead there ahead of your presentation and say that you're actually presenting part of what's been your master thesis. So that's really cool. Yes.
Yeah. It's a small part, but hopefully it'll connect nicely to the meetup.
Thank you. Yeah, the stage is yours. Hit it away.
All right. I think I'm getting some audio there. So can I start? All right. All right. Thanks, Magnus and Adabit and Func Prog, Sweden, for the introduction. So I'm going to talk about this little concept here of polynomial functors and why it's a jackpot. And I'm here representing Adabit. I work there as a functional programming consultant, and I'm also showing off some of the work I did as part of my master's thesis at Chalmers University. All right. So okay. So a little bit of background on me. I'm a programmer. That's what I do by trade. And I've loved Haskell, the programming language, ever since I first came across it. I think it's quite a beautiful language. It's just include a little snippet of code here. A lot of people are going to be familiar with that. And I've also had a sort of a parallel or dual love or interest. Sorry, I'm getting some audio. I'm getting some. Sorry, I'm hearing some audio back, so it's a little distracting. But all right. So anyway, some background on me. I'm a programmer. I've always loved the Haskell programming language ever since I first came across it in university, and but I've also had this sort of parallel interest, you could say, in complex systems, which are systems that basically have simple parts, but when they combine and are allowed to interact, the simple parts are allowed to interact with one another, they give rise to some complex behavior, like this little diagram shows of emergent global structure. And I've always had this sort of nagging feeling that, well, Haskell is a language that is kind of known for abstracting a lot of stuff away and finding and distilling different patterns of abstraction in different, programming contexts. And complex systems is also kind of about these abstract structures or some structural similarities that just show up in physical systems in the real world. It's a very physics-oriented discipline, but they've always had this kind of thing in common of, similar abstract structures appearing in different places. And this kind of led me to find a very nice synthesis of these two fields, these two interests, which is in the topic of applied category theory. A lot of people might have heard that Haskell is very influenced by ideas in category theory. And I'll get into what applied category theory is, but the way it connects directly is that it's basically the topic of the master's thesis, and I'm going to show a technique or this particular category and how it can be used to give you a better sense of this connection. So what you need to get the most out of this talk, some background for the reader, for the people watching, is I hope you have heard of category theory before. It's I'm not going to go into any heavy categorical stuff, or I'm not going to go into any more detail than necessary for the point I'm trying to make. But it's good if you know that it's about objects and morphisms between the objects, and crucially, it's about what happens when you compose morphisms from one object to another. So in this little diagram here, we have a morphism or an arrow or a map, it's also called, from A to B, one from B to C, and that forces the existence of G after it, the composition of these two arrows. Another thing that will help you get the most out of this is to know that there's an algebra of types or sets. Really, you can think of types as a collection of values. So they map pretty nicely to sets in mathematical set theory. And the previous speaker, Adrian, actually did me a big favor in explaining and going into quite a bit of detail for what it means in programming for the fact that this algebra of types exists. This is a very deep fact, one of my favorite facts about the universe. And also, I hope you are familiar with Pascal's basic syntax, and this, so declaring some data types here and defining function. And I also hope that you can look at some Agda code and not be, sort of freaked out by it. It has a pretty similar syntax to Haskell, but it has dependent types, which is basically, you can kind of think of it as a super Haskell. That's how I market Agda to my programming friends. It basically means that a type of value can depend on on some other type's value. And this is some Agda code declaring a record here, so a product type. So starting with some motivation for why apply category theory is relevant at all. So category theory, pure, is about patterns in different areas of math. The field was invented because people would find, there's this theorem here in group theory, and there's this other theorem here in topology, and there's this other structure over there in abstract algebra, and they kind of remind, there's a sense in which they remind one another they look similar. And is there a way to make this connection precise so it doesn't just live in this sort of fuzzy intuition space? And it was very successful, and this was invented, I think, in the 50s. And now it's a field of math on its own right. And what I would say is that there is a categorical mindset. It's a way of seeing things. You focus on compositionality, what it means for two relationships, or two, technically speaking, they're morphisms or maps, but these arrows that go in between objects. What happens when you compose them? What happens? What does it mean for these arrows to compose and have some meaning in a field over here, to them having this, to them preserving composition, or keeping their structure as you translate between fields. And applied category theory is a pretty young field, I would say. It's about employing this way of seeing patterns into other fields. So not just pure math, not just algebraic geometry or topology, but things like game theory, chemical engineering, economics, statistical physics. The list just goes on and on. If you look for applications of category theory on Google, you'll likely be overwhelmed. This way of seeing, I like to think of it as conceptual plumbing. It's like you're sticking concepts together, and you're focusing on how they fit together and not on what things are. There's a great tweet here about what it does to your thinking. for the categorical outlook on the world, on science, on knowledge. And there's these great talks here for very concrete examples. They go on to a lot of detail of what this means. One is just how it helps you think about a problem domain, and one is just in software engineering examples, really. And oops, I have to zoom out, I guess. And by representing things in these categorical terms, they can be seen as a part of a larger context or a universal language that is very formal and very precise. But this can be really hard. There's a quote here. This is on the category theory Zulip, which is like a Discord or a public chat room. And a lot of working category theorists are there. And this guy here, John Baez, is a legendary figure in this field. And it sort of speaks for the statement lands, because sometimes the connection between how you can formalize something in categorical terms is just really far away from the reality of the model. It's like the particular abstraction that the thing tends to map to, or sometimes it's just not clear and you can't really use it. Except that sometimes a really, really good and powerful abstraction or way of seeing, to keep with this theme, comes along. And this is polynomial functors. And I'm giving you a list here of different things that it either models directly, or it applies to, or is related in more or less straightforward ways. These here are some visualizations of them. I'll explain what this means in a second, but this is this list here is non-exhaustive. I mean, people are finding new applications of this concept all the time. And what I hope to give you from this talk is just an inkling or some instinct that we're onto something. The first time I came across this concept, I didn't understand what was going on. It was hazy and confusing. I'm like, how does it work? So I don't expect you to come out of this like, yes, I know I can use polynomial functors anywhere now. I'm trying to give you a sense of their power. But before I introduce polynomial functors, I just want to give a little more perspective on regular functors. So functors are this concept from category theory, which is for our purposes, we'll just talk about the category of sets or types. So they act on types, right? Like a function sends a value to another type, right? Like this function here sends every integer to its successor. So 1 gets sent to 2, etc. A functor sends a type to another type. In the case of the list functor, which is the one most functional programmers are going to be, it's a pretty straightforward example, I think, or I hope. The type int gets sent to the type list of int, so list of integers. String gets sent to list of strings, etc. And functors also have the property that they act on functions on the original type to functions on the target type of functor. So if you have a function that is a type int to string, then fmap of that function, which is applying the action of a functor on the function, is going to have type f of int to f of string. In this case, f would be list. And there's some drawings here to help you visualize this. So what are polynomial functors? They are a specific type of functor. They're a specific subset of them, we could say, that send the source type to a target type that combines the source in a limited way. These are basically the only operations that we can use. It's summing, multiplying, and raising to the power, exponentiating. This is in the sense of the Curry-Howard isomorphism, which is that what gives us that algebra of sets or of types that algebraic data types are based on, and that Adrian actually explained in his talk. And a convenient way of representing this, representing polynomial functors, is as dependent pairs. So it's one set, and then for every element of that set, it's another set. So there's a visualization here. These are called corolla forests. Corollas are trees of depth 1, so these little forests of little trees here. And this one has a set of so-called positions, and each position has a set associated with it. So this one position has a set with 5 elements. This other one has a set of 2 elements. This other one also has a set of 2 elements. This one has 1 element. And there's 2 ways to, here's 2 examples of ways to write these. One is in Haskell. This is a regular data type. You could derive the functor instance for this automatically. So this one is one type. The first type value constructor has 1, 2, 3, 4, 5 copies of y, the thing that the type that the functor acts on. Second one has 2, etc. And you can also write these algebraically. And then importantly, the numbers here mean sets with that many elements. So this is y to the power of the set of that many elements. We're only using the stuff that we're allowed to in this setup here. The set of positions is a set of sum ends in an expression like this. So this one has 4 sum ends. This one has 5. That's the set of positions. And the direction at a given position is the exponent of that sum end. So this is a polynomial functor. And we can map between polynomial functors. If you know a little bit of category theory, or perhaps you've done some more advanced Haskell, these mappings between functors, you might expect that they're natural transformations. But they're actually called, for our purposes, we'll call them dependent lenses. And yes, there is a connection with Haskell lenses, but don't worry about it. That's I can answer questions about it later if anyone cares, but we're not concerned about fetching data inside of deeply nested data structures here whatsoever. It's just to think about them as natural transformations. And the dependent lens has this map forward on position. So this is represented by these 4 arrows here with our previous example. And then for every one of these mappings, you need a map back on the directions at wherever you landed. And if we look at this map in Haskell, this is what we see. These are from our Haskell definitions before. This is exactly the map here, actually. So the first thing is you pattern match on the constructor of the first functor, the first constructor, and you have to choose one of the constructors in the target functor, which is Q here, and that's the first step in your pattern match. And then you need to fill the slumps of that value constructor. If you remember, QA has 3 directions, and that's what is represented here. So QA 1, 2, 3. So for each one of these, you have to choose one of your Y values to fill it up with. And this is how the map back is working. For every one of these slots, you have to pick one of 5 different choices. And the same for all the other constructors. So functors, polynomial functors as objects, lenses as morphisms. This gives us a category, the category poly. But the Haskell way of working with these polynomials is pretty limited, because polynomials can have any type as a position or sum end. And in the case before, we were just showing, they were finite types that we know every element of the type, so we can just work with them directly. But this is a coherent expression. This is a polynomial functor, but it's not really clear how you do this in Haskell, at least not to me. People are trying to do it. Iceland Jack is a more or less well-known figure in the Haskell ecosystem, and every once in a while he posts stuff on Twitter. I'm trying to follow the source that I follow for my master's thesis, but it's not clear how to do this. I guess this is a valid representation, but for me at least, it's not clear how to. I don't even really know what I'm looking at. and lenses or mappings between these functors are going to be even harder. So enter the AGDA programming language, which is dependently typed. This is really a much more natural way of expressing the category poly, that's sort of polynomial ecosystem. And AGDA looks pretty similar to Haskell, I would say. This record is basically except we can give names to the field, so it looks a little nicer. I think it's more usable. And this is a polynomial, so you have a set of positions, and for every position in this set, so this is how dependent types come into the picture here, you have another set. So if you give me one of these positions as an argument to the field direction, I'll give you back a set. And a lens is also a dependently typed construct. And you have, again, you have two polynomials from and to. There's a map on positions, position from to position to. So this is the map on the this is the map going forwards. And then there's the map on directions going back. So given that you start at one position, and given that you have a position at which you start, and you have a direction at the target polynomial at a mapped position from where you started, I'll give you back a direction in the one you originally started. So this is the map backwards. This might be a little tricky to wrap your head around, but again, it's about the inkling. And after working with this for a while, you start to wish every programming language had dependent types, because you often forget how much power you have actually. It's so much power that AGDA can actually be used for proving theorems, just stating mathematical theorems and constructing proofs. And this is also part of my master's thesis, to prove a bunch of categorical properties of the category poly. But now I want to show enough math, or that was enough math. I want to show how this is actually useful and apply to something. And the application that I know the most about, that I've written the most examples for, are dynamical systems. So a dynamical system is a very general, sort of loose thing. It's defined as basically a process that evolves in some state space. And so the state space is going to be a set also. In this case here, this is just a little picture showing the dynamics of a particular system. And this system, if you start with some initial condition or some initial state, it's going to traverse the state space in a certain direction. In this case, it's like a two-dimensional. I think this is R squared, so it's like the state space is pairs of real numbers. But there's also such a thing as an open dynamical system. So what if we don't want to just let the dynamics run in time? We also want a notion of providing an input to the system at every time step. This is showcased here. So when you're on state 0, if you give the output, if you give the input 1, then you're going to traverse to state S1. But if you give the input 0, you're going to stay at S0. And this is a little automaton that is sort of gives the idea of what an open dynamical system is. And one way of formulating this is as a Moore machine, which is a very general kind of thing. Many things can be modeled in terms of Moore machines. There, if I understand correctly, there's still study to this day in automata theory. And Pauli's dependent lenses, the thing that we gave the data for a dependent lens, actually models Moore machines very well. You don't even need all the power of Pauli. You can get away with a non-dependent version of it. But just to stay in the Pauli land here, lenses of this form. So if you have some state type y, some state type multiplying your variable y, and then raised to the power of that same type, you have a lens from this thing to some other expression here, so an output type times y raised to an input type. that can be interpreted as a Moore machine or an open dynamical system. And so here's a little box showing this. It's like it's a this is something like this would be, so this is the output type. So this would be IO int multiply y raised to the power of top, and this is the unit type that has only one inhabitant. And one thing we can do is put systems in parallel with this operator here, with O times. This is called the parallel product. And this is a categorical construct, but this is the only, I'm pretty sure this is the only categorical construct that I'm gonna, we're gonna need for the rest of the application. So then if you have a polynomial B or P and Q, and P is, has AB in its raised power, so that's its input type, it's pairs of A and B, and its output type is D, and you have Q like this. If you put them in parallel, then you get something that takes an A, a B, and a C as inputs, and it produces D, E, and F as outputs. And then, so that's polynomials, and then lenses can be used to wire systems together. So, and this gives rise to a new system. So the idea here is that you have this inner box, which is the dashed line here, and a lens from this inner box to this outer box. This outer box is the expression for it is given here. Takes A, B, C as inputs, produces A's. This wiring pattern itself is a lens in a very precise and specific way. I'm not going to show the code for this. I can if someone is really curious and wants to see what this looks like in code. But this does reduce to just those two functions that compose a lens, a map on positions and a map on directions. Here's another example of a different wiring pattern between the same two polynomials. So it's just an example of a different lens. And some concrete examples of this, of these, the lenses that actually correspond to dynamical systems, are these two here. So this is a little, we call them wiring diagrams for a Fibonacci sequence generator. This is one of the first examples in the book that I followed for this work. So you have one system that just its only responsibility is to sum its two inputs and then spit that result out as its output. And you have another one that just takes its input, takes an input and produces that input as an output always. This is the identity function modeled as a dynamical system. And if you wire these two systems in this particular way, then what you get as an output of the outer box here is the Fibonacci sequence. So you're summing. It might not be obvious how that is the case now, but again, it's about the idea of the expressive power of this sort of setting. There's another example which is very fun, which is a Turing machine. If you remember your probably some introductory class on the history of computer science. So a Turing machine is made up of an infinitely long tape that can have a bunch of symbols on it. It's called the alphabet set. And it has a processor that interprets these symbols in some way and runs some internal logic. This actually works. You can model a Turing machine in this way with such a wiring diagram. And here's a reason why I didn't actually want to show any Agda code, is because it perhaps would need too much context to explain and to go into, and I'm trying to give a high level idea. But if this means something to you, you can copy this code and run this fiblist variable here. Is actually contains the Fibonacci sequence. But here's a bigger example that, again, I'm not going to go into the details, but something that actually uses even more of Poly's power. It's that of a kind of neural network called reservoir computers. And the thing about a reservoir computer is there's a little schematic here showing what it is. And the main thing about it is that it has three basic stages. So when you want to run a program, when you run a reservoir computer to predict some input, as you might know, neural networks learn to reproduce or learn to recognize inputs and produce consistent outputs based on some input. There's a training stage, and then there's something called a touching stage, which is specific to the training algorithm of a reservoir computer. And then there's a going stage where it's actually predicting. So our box is actually changing its wiring pattern. And this is where the category poly as modeling dynamical systems really shines. And there's also code written for this. And this power of expressing dynamical systems that can connect to different things as time goes on I think is just extremely cool. And there's just an endless array of things that can be modeled in such a way that they just change the wiring pattern in time. And just to show that this actually did work is on the left here we have a dynamical we have a system called the Lorentz system. It has a property, it's called a chaotic dynamical system, and that basically means that it's really hard to predict how it's gonna traverse its state space. In this case, it's R cubed. It's a 3D system, so it's 3 tuples of real numbers. And reservoir computers are used to train. They're trained on values of the Lorentz system in order to be able to predict them. And this is the implementation that I did for my master's thesis, and it just shows the prediction as time goes on. After you train the reservoir, it can actually predict the dynamics of the Lorentz system, so the outputs that it gives in time. And there are more intricate ways of representing the changing wiring patterns in neural networks. As I know, coalgebras in Poly are very relevant to that, but I don't really understand them well enough to explain them to you, unfortunately. But this is just this picture here was actually generated by some Magda code, and it's real. It's a real program that was just uses the category directly in a very ergonomic way. And so what else could we model this way? I mean, I gave a very exhaustive, very potentially overwhelming list of examples in the beginning, but here's some more ideas. I've been thinking a lot about modeling microservices in terms of polynomial functors. Microservices are these they are little boxes that speak to one another. They provide input to another one's output, or output to another one's input. They can change their wiring patterns, and microservices talking to this system at this particular state, and then it's not, and then it's changing throughout time. Front-end components are also a good example of this, I think. I haven't explored this line of thinking totally yet, but I've been doing a lot of Halogen, which is a framework in PureScript, where components are modeled it's very composition. So components own their own little state inside them that can be, and they have an input type and an output type. It's shown here, and they have a monad in which they run, and this is not showing the state type. This is part of a different part of the application, but in principle, they are this sort of object where they have a state, they have a notion of what it needs to be a state for them, notion of an input, a notion of an output, and they connect in this way. And hardware circuits are just lend themselves very naturally to this sort of exploration, also to this sort of modeling. And there is some categorical work on formalizing circuit diagrams. But I also still don't know that much about them. But yeah, this is a very, very small list of examples. Again, going back to the theme of the talk, it's about giving imagination, as David Spivak, one of the authors of the book, says. To, oh wow, yeah, I wonder what things I'm working with that also sort of fit this general pattern of communicating parts that can change their connections and go in different, have different wiring patterns to them. And that is actually all I have for the talk. And to sort of justify, to give finally explain why I called it a jackpot, is because this is actually a quote in the book. The category poly is a jackpot. Its beauty flows without bounds. And again, didn't understand it the first time I read it. Then I started actually using it in my work, and I couldn't agree more. This is from the authors of the book. This is the main source I would like to point you to. There's also an entire free course, just a playlist on the book. They go through the entire thing. It's pretty heavy on the category theory. It might take several watches, but they do, I think, a good job of consistently keeping it with the connecting it to the intuition behind these concepts. And more generally, the Topos Institute YouTube channel is just fantastic. I can hardly recommend it enough. If this stuff sounds interesting at all to you, I suggest going down that rabbit hole a little bit. And yeah, you can find all the code for my master thesis. You can find in the GitHub, and in the link here. But yeah, that's all I have for tonight.
Thank you very much, Andrea. Thank you. Very interesting. I actually started to read your master thesis in the beginning, and as I said, I think I need some kind of framework before I just go into it.
Yeah.
You gave it very good. Thank you very much. We have two questions in the chat, or one thing, like now we got to clarify object in category theory, and that it's not object in object-oriented programming.
Yeah, no, it's not. So I'll go back to the little diagram. I thanks for pointing that out. I didn't even connect those dots there. So an object in category, in this case, the objects are A, B, and C, and the arrows are F, G, and F after G. And there's also some identity arrows that are important for, well, they're important. But the object has nothing to do with objects in object-oriented programming. The idea in category theory is like I was trying to stress, it's about the compositionality. So the objects are supposed to be totally abstract or meaningless in some sense. What matters is the relationship between the objects and the patterns of relationships that form, how we can study those mathematically. The A, B, and C here are kept as abstract as possible. I mean, the arrows are also kept as abstract as possible, but in this particular diagram. But the thinking in category theory is focus on the morphisms. The objects are just there to basically give endpoints to the morphisms. Yeah. So thanks for thanks for catching that.
Yes. Thank you again. How come you come into Haskell programming?
So I got into Haskell. I took a course in university. I went to University for Computer Science back in Brazil, and I took a course called Paradigms of Programming, or Programming Paradigms. And they started just straight away with Haskell, and at that point we had like I think 1 semester of some basic C, maybe 2, and I was basically drawn to it because it really destroyed me. I didn't understand the concepts, and I remember the TA even couldn't explain what a monad was, and I was, oh, but people still use this and they swear by it, and how come the code looks so elegant and beautiful? Well, there must be something to this, and I just kept digging, and yeah, I was hooked.
It's like this mystery you have to unravel.
Yeah, exactly, an adventure.
Yeah, and then you kind of get. I mean, you continued from Haskell into this, like starting talking about category theory. Is it also like the more you learned, the more you have to, you know, you have to drag this rope. Like, where does it go? Where does it go? where's the end? Where's the end door?
Yeah, and the amount of directions you can go just grows as you pull the rope. It just grows more and more. It's an incredibly deep set of subjects. Yeah.
How do you, if you would give an advice to someone that want to learn Haskell, looked at Haskell and felt, shit, I don't understand jack shit of this. Where would you start? Like, to, progress into learning Haskell?
So I think there's two different ways of answering this question. So the people, I'll choose one of them, which is people tend to associate functional programming with Haskell because it's purely functional. It's in computer science curriculums, and it showcases the aspects of functional programming the most. It sort of forces you to do it that way. But what I tend to recommend to people is actually, if you want to learn functional programming, don't start with Haskell. Start with Clojure. Clojure is it's also a functional programming language, but it is dynamically typed. People get stuck on Haskell trying to print something to the screen, or how does the IO monad work? How do I get something out of a monad? And it's just not the right way to think about it. If your program is running on a processor, it is in a monad. Don't worry, you just have to inject the behavior in there. But this is too much to throw at beginners, I think. They get sort of lost in the type system. So I think, and Clojure doesn't have any of that. I think it's a much more beginner-friendly language that will sort of train you to think in functional terms. And I think the transition to Haskell and the type system and monads and all that there is going to be more natural.
Yeah. Kind of agree. I started myself in other languages and leaned into Erlang. It was quite natural from some languages. More, you talked a bit about Agda. How come you was that part of the category theory? So you had Haskell, you had this background, you went into category theory, and now Agda came to you, or you came to Agda?
Yeah. So the Agda thing is interesting. So Agda is actually developed at Chalmers, and I didn't know this. I went for the master's. My master's is in complex adaptive systems. Actually, I didn't connect the dots that the place where I was doing my master's program was actually a big home for functional programming in Agda. And but I still wanted to connect these two things, like the sort of the Haskell / categorical way of seeing stuff with complex systems. And the Agda presence here is at Chalmers is just so strong that it was kind of a natural fit. And once the authors of the book just said, don't try to just represent this stuff in Haskell. It's gonna be too hard. Like I showed, it looks weird pretty quickly. Use a dependently typed language like Idris. So Idris was the first thing I played around with dependent types. I knew they were around, but I never tried them. But then Agda was much more natural, and because of the fact that it's developed at Chalmers and so many people who know about it here. So yeah, I think that's how I got into it. There was no other way really.
Yeah, we had some people here shouting or saying in the chat, not shouting, but saying in the chat you could also go from Elm into into Haskell, and then some other people
Mhm.
agreeing with you. Like I started out in Clojure and then went into looking and doing the same thing in Haskell. Yep.
Yeah.
So thank you very much again, André. Very nice presentation. Thank you very much.
Yeah. Thanks
Yes.
for having me.
Yeah, you're welcome. You're welcome back if you want to present more concepts from your thesis. Yeah.
I'd be delighted to. Thanks.
Yeah. Great. And with that, we'll end tonight's meetup, and we'll see you again in August. We'll announce like in a week or two when we do the dates in August, September, and then as I said again, if you're in Stockholm in October, come and see us live in Kivra. With that, have a nice summer vacation, everyone, and see you back in August. Bye.